Hello viewers, welcome to my channel KK Concepts of Electrical Engineering. Reflection of electromagnetic waves. Consider a uniform plane wave propagating in a certain medium at a certain velocity. As long as there is no change of medium, the propagation continues uninterrupted. If the traveling wave encounters a different medium with different values of conductivity, permittivity, it is found that the entire wave is not transmitted into the second medium. A part of the incident wave is sent back at the boundary separating the two media, and only the rest of the wave is transmitted through the second medium. This phenomena, by which a part of incident wave is sent back at the boundary, is termed as reflection. Media 1, media 2, this is incident wave, and this is reflected wave, and this is refracted or transmitted wave. This is having mu, epsilon, sigma 1, 1, 1, since the medium is 1, and this is mu 2, epsilon 2, sigma 2 for the second medium, and this is having the velocity v1, this is having the velocity v2. Reflection of electromagnetic wave at a perfect conductor surface. Consider a uniform plane wave traveling through a perfect dielectric media in positive x direction. Let the incident at the surface of a perfect conductor. At the boundary surface between the perfect dielectric and the perfect conductor, the incident wave may be either normal or oblique. Now this is a perfect conductor. Is equals to 0. So consider normal incident. Now let the incident wave be normal to the reflecting surface. Since the first medium in which the wave is traveling in the positive x direction is a perfect dielectric, this is alpha, that is attenuation is 0, and gamma equals to j beta. Now the incident wave mathematically represented in this is E incident is equals to Ei is the amplitude, e to the power of minus j beta x. The second media is a perfect conductor for which depth of penetration delta equals to 0. Since electromagnetic energy cannot be transmitted through the perfect conductor, there is no transmission of incident wave through the second medium. The entire wave is going to reflect into the first medium at the boundary surface. Reflection wave is represented ER reflected equals to ER e to the power of j beta x in the negative x direction. At the boundary surface, that x equals to 0, the tangential component of electric fields are continuous according to the boundary condition, which means that T tan 1 equals to E tan 2. But inside the second medium, E tan 2 equals to 0 because it is perfect conductor and there can be no electric field within it. Therefore, E tan 1 equals to 0. At x equals to 0, E incident plus E reflected equals to 0, which means E incident equals to minus E reflected. Consider a point at a distance of minus x from the boundary. At a distance of minus x, let it be. Total electric field E equals to Ei e to the power of minus j beta x with the incident wave plus Er e to the power of j beta x is the reflected. We know that E reference equals to Er e to the power of j beta x, that equals to minus E incidence, whichever it is, Ei e to the power of minus j beta x. Now substitute this in this, then you are going to get E of x by generalizing equals to Ei e to the power of minus j beta x minus Ei e to the power of minus j beta x. Now you can write this E of x equals to, take that Ei common, then e to the power of minus j beta x minus e to the power of minus j beta x. This we can write as minus 2j ei sine beta x. Now, multiplying ex by e to the power of j omega t to take into the account the time variation and considering only the real part, we can write this as e of x comma t equals to 2 ei sine beta x and sine omega t. The resulting waveform, which is the sum of incident and reflected waves, is standing wave, which is shown in the figure. The equation represents the standing wave. This is 0 at 0 and the amplitude is twice the amplitude of the incident wave. Now consider the magnetic field H. There is no transmission of energy through the second medium. It is very essential for reversal of energy and the boundary surface that the reflected wave magnetic field strength has the same phase as that of the incident wave. If the phase of both electric field and magnetic field are reversed due to the reflection, there can be no reversal of energy. Hence, Hi equals to Hr for magnetic wave. Then H of x equals to H of I e to the power of minus j beta x plus Hr e to the power of j beta x. Since the Hi equals to Hr, you can write this as Hi take the comma e to the power of j beta x plus e to the power of j beta x. Now this can be written as 2 times Hi cos beta x is equals to H of x. When you consider the time variation, H of x comma t equals to real part of H of x e to the power of j omega t, that equals to 2 Hi times cos beta x cos omega t. When you draw the waveform, you can observe there is a phase difference of 90 degrees between the total electric field and total magnetic field. The electric field E is at x equal to 0 starting at 0 point, whereas the magnetic field H is starting at the peak value when x equal to 0. The phase shift is 90 degrees. Oblique incidence. If the incident wave is not normal to the boundary surface but makes an angle with the normal to the surface, such incident is termed as oblique incidence. Consider oblique incidence. The electric field intensity vector may be either perpendicular or parallel to the plane of incidence. In the first instant, the electric field vector is aligned parallel to the conducting surface and it is said to be horizontally polarized. In second instant, the electric field vector is aligned perpendicular to the conducting surface, hence the field vector is said to be vertically polarized.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.